Hello everyone. I'm Zehua Ma from USTC. I'm going to present AnisoTag, 3D printed tag on 2D surface via reflection anisotropy. Certainly, let me begin by sharing our motivation for conducting this research. As a commonly used HCI application, machine-readable tags, such as barcodes and QR codes, have found widespread use in marketing and brought significant benefits. Meanwhile, the market for 3D printed products is experiencing rapid growth. On Amazon and Etsy, thousands of 3D printed products, mainly fabricated by individual creators, are being sold. Thus, we pursue a tagging system for 3D printed product. In this scenario, this tag should be unobtrusive for aesthetic appearance, easy to fabricate for individual creators with basic device and materials, and better have a lightweight extraction process for potential real-time extraction requirement for retail scenario. Up to now, there are plenty of schemes for tagging 3D printed objects. Some schemes are visible to human eyes. The visible modification allows the embedded information to be easily captured by consumer-grade devices and can be extracted using relatively simple algorithms. For invisible schemes, they usually encode data by imperceptible modification. Yet they commonly need large devices or complicated algorithms to enhance imperceptible modification and then decode the data. For example, invisible layer code and infrared tags require infrared materials at the time of fabrication. When extracted, layer code, infrared tags and air code require special camera equipment, and all of these solutions require image processing algorithms to enhance the data signal. To balance the visual quality and extraction complexity, the data on AnisoTag is encoded by the microstructure on the 3D printed object and would be extracted by its reflection anisotropy. First, why there exists microstructure on 3D printed objects. The left image is the schematic diagram of FDM 3D printing process. The material is fed into 3D printer and extruded as parallel plastic line. These lines compose a 3D printed layer, and then layers compose the target object. Because of the melted material and the trajectory of extruder head, there are unobtrusive microstructure in 3D printed object, as shown in the enlarged view in the right image. Then, the surface microstructure determines the reflective property. For one object has flat surface like the left image, it usually has isotropic reflection property. Yet for the object whose surface consists of the microstructures, it would have reflection anisotropy. And the appearance would depend on the conditions of the lighting and viewing environment, just like the right image. Now I present the proposed AnisoTag. As shown in right image, the microstructure generated by common setting has a certain reflection anisotropy, but its detection is still a challenge for inexpensive hardware. For easy extraction, we need more obvious reflection anisotropy that need not complicated device or algorithm. Thus, we proposed SCS microstructure, generated by slightly modifying the FDM 3D printing process, whose reflection anisotropy could reflect collimate laser beam to an obvious illumination pattern. Then, AnisoTag encodes data by SCS microstructure with different angles in the encoding region. Take the right image as an example. The AnisoTag has many encoding regions. In each region, we encode 3 bits, that is, the microstructure has 8 possible angles. On one credit card size region, AnisoTag could encode 51 bits data. We propose a simple G-code tool to generate the G-code file of AnisoTag, which instructs a 3D printer to fabricate SCS microstructure. For fabricate 3D object with AnisoTag, we can combine the G-code file of AnisoTag and the target object, and 3D print them together. But how to leverage the reflection anisotropy to extract the data? First, we model the reflection process of SCS microstructure. According to this model, we could precisely establish the mapping between the infilling angle of microstructure and the reflected illumination pattern. Thus, we could detect the obvious reflected illumination pattern, the red curved line in images, to determine the data encoded on the microstructure. Furthermore, we derive two characteristics of reflected illumination patterns. First, keep the other setting the same. Whatever the SCS microstructure angle is, the reflected illumination pattern would cross the same fixed point. Second, we found that the reflected illumination pattern is one truncated conic section. Then we could simplify the detection task. We draw a detection circle, shown as the black circle in the left image, around the blue fixed point. Then, by detecting the intersection points between the reflected illumination pattern and the detection circle, the pattern could be uniquely determined. In this paper, we chose the cheap photoresistor to compose the detection circle. This is the proposed detection prototype of AnisoTag. The light source is a laser pointer pen. The detection circle of photoresistors detects the illumination pattern reflected by AnisoTag and converts the light intensity to voltage value, which would be transmitted by circuit to one PC to decode the data. After AnisoTag is swiped from one side to another, we could extract the data embedded on it. The evaluation illustrates the usability and accessibility of the proposed AnisoTag under various 3D materials, including different colors and types. And for different 3D printers and illumination settings, AnisoTag still perform well. Thank you.